And now for our final speaker of the day, Kirill Zatrimailov is going to be talking on the Wormhole-Warp drive correspondence. Kirill is a researcher at I don't know how I got this one, Università degli Studi di Bergamo in Dipartimento di Ingegneria e Scienze Applicate. His research covers University of Bergamo, thank you, Sonny. His research covers quantum physics, elementary particle physics, and cosmology.
Hello, everyone. The topic of my talk is on the Wormhole-Warp drive correspondence. So first of all, let me briefly review what a warp drive is from the mathematical point of view. A warp drive is a metric of this form, without intrinsic curvature and without the Lebesgue function. So with the shift vector of this form. So we have a background metric and this sort of, and the warp drive is a kind of a solitonic perturbation moving on it, perturbation of the metric. This function f is a function usually of Bell type, like a Gaussian, for instance, and the Eulerian observers inside the bubble are in free fall, so they are in an inertial reference frame. Now, the warp drive can be compared to a raft moving on a river against a current, and so the velocity of the raft is the total velocity of the raft depends on its own velocity and the velocity of the current, the river. Now, one very well-known result from general relativity. Yes. One very well-known result from general relativity from the 1920s, derived by Penleaf and Gallstrand, is that if we perform a coordinate transformation in the Schwarzschild metric, we can take it to a metric of this which has this warp drive form. So this becomes this, and which is a warp drive type metric with this background shift vector. Now we can embed an actual warp drive moving through a black hole. So we can substitute beta like this. But the problem is that a warp drive bubble would likely be destroyed by the Hawking radiation from the black hole. So in our own work, we generalize this result to Morris third wormhole metric. The Schwarzschild metric is a specific type of it. So a generic metric of this kind can be transformed in the same way. It yields this kind of metric, which is almost like a warp drive, but not quite. We have this form factor f in front of the r, which makes it quite cumbersome in Cartesian form. And so this form factor is basically the product of the 0, 0, and they are components of the metric tensor. And if it's in this case, we can also embed the warp drive in the same way. However, then we also have to make sure the wormhole is traversable. So there is the flare out condition, the throat condition, and the absence of horizon. The throat condition says that the expression in the denominator should become 0, at the throat, and the absence of horizon says that e to the point of 2 phi should never become 0. So basically taken together, these two conditions mean that the form factor has a singularity at the throat. This is a potentially problematic feature, but we have computed the Kretschmann scalar for this metric, and one can see from rough estimates that it's non-singular at r equal to the radius of the throat, which means that this singularity is likely not physically relevant. However, for now, this is a purely theoretical construction. As you all know, we have recently observed black holes, so they've moved from the realm of theoretical into the realm of observable. And as for the warp drives and wormholes, they are just conjectures for now. But there could be some interesting options to have a look at this in in tabletop experiments through an approach which is known as analog gravity. Analog gravity refers to the fact that some kinds of fluids without rotation, including Bose-Einstein condensates, produce this kind of effective acoustic metric, which on which the velocity potential propagates. The velocity potential is the analog of the scalar field in this case. Then by performing the Penleaf-Gallstrand transformation in the opposite way, we can bring it to this form. And now for a particular radial velocity profile, 1 over square root of r, we recover the Schwarzschild metric. This has been, in fact, the Schwarzschild wormholes have been reproduced in experiments. Some rough analogs of them one-dimensional models. This work was done by Jeff Steinhauer and his collaborators in Israel. It's a tube of Bose-Einstein condensate of atoms, which flows, and in one region the velocity of the fluid is subsonic, and in another region it's supersonic. The border between them corresponds to the black hole horizon. However, if we want to see the embedding of the warp drive, so the black hole is a rotationally symmetric system, and the warp drive breaks this. The warp drive which enters the black hole wormhole breaks this rotational symmetry. So to see this dynamic, it would be best to have at least a 2 + 1 dimensional system. These kinds of proposals exist as well for systems like photon superfluids, for example. Now the more tricky question is whether we can reproduce a wormhole in analog tabletop experiments. As you see here, this metric, this is the inverse of this. So if we want to have two distinct metric elements, we need to introduce additional degrees of freedom. So see which is the speed of sound, not the speed of light in this case. We have to make the C and the background density rho to make them vary. And then we can perform this again, this substitution of variables to arrive at this kind of metric. So from this we can try to construct something like the Morris-Thorne wormhole. Of course, without the topological features, which is not possible in a lab. But one can hope that possibly one can reconstruct the physics near the throat. This the variations in the speed of sound and the density of the fluid can be achieved through the application of external magnetic fields, like, for example, in Feshbach resonance. And so this is what we are looking into right now. However, this is not this is not all that I wanted to tell you today. Now, if we come back to this kind of metric, and forget about the wormhole, so now we assume a background, a Minkowski type background, and this is just a type of a more generic type of a warp drive metric. Now we would have to these kinds of metrics, since they also have the ellipse function equal to 0, then they can the observers on time like geodesics would still be at rest, and then for this particular case we have a curved intrinsic metric of this form and the shift vector of this form. Now, f is no longer the form factor related to the wormhole, but just a local curvature that depends on the location of the warp drive. So it moves with the warp drive. It would be interesting then to see how what happens to the energy conditions for this model. The energy density is given by this, the sum of the intrinsic Ricci scalar curvature plus the square of the trace of the extrinsic curvature tensor minus the square of the extrinsic curvature tensor itself. One can do a rough estimate of the energy density by computing an integral of it over the whole space-time. Recently, a no-go theorem has been proven by Santiago, Schuster, and Visser, according to which if there is no curvature and there is no time dependence in the metric, then the energy density is just a total divergence of a quantity minus the square of a quantity. The first term vanishes upon integration over the whole space, and the second term is manifestly negative. So these kinds of warp drives always violate the null energy condition. However, in our case, we also have the terms coming the time dependence from this contribution in the extrinsic curvature tensor, which amounts to this. But then at each xs is the coordinate of the warp drive at each time moment. But then since we are not interested in integrating over time, then at each particular time moment, we can set the origin of the coordinates to the location of the warp drive, and thus this term becomes 0. So in this coordinate system, in this the intrinsic curvature is given by this expression, and once we integrate it, we arrive to that. So the properties of this expression depend on the particular function chosen. The function far away from the warp drive, f should be equal to 1 to yield asymptotically Minkowski space-time. And for example, if we take a function of this form, then the integral yields this, and if we make this a constant r, we can make it arbitrarily small, and thus we can make this contribution to the energy density integral positive and as large as we want to. Of course, this should be taken with a grain of salt for now, because this is just a very rough estimate. one should do a detailed analysis of these types of metrics to see what happens to the null energy condition. However, this means that at least these kinds of metrics are important to investigate further, and they may be able, if not to bypass, then at least to alleviate the need for exotic matter. So our conclusions are the following. We have found this mapping between Morris-Thorne wormhole metric and quasi-warp drive type metric with the form factor. And we are hoping to that something like these models could be observable in analog gravity experiments, and we are also, for now, we are also looking into this new type of warp drive metric, which which may be able to reduce the amount of exotic matter needed for a warp drive. Thank you for your attention. Any questions?
It's known for warp drives that you need to violate the null energy condition. This is similar
Yes.
for wormholes. There's a paper published not too long ago, and it's on having traversable wormholes. And to have that, you need a negative energy density, just like the warp drive. And basically, their argument is like take a scalar field theory, couple it on the two boundaries of the wormhole throats, and then there's a gravitational back reaction of the wormhole, and you get like a negative energy stress tensor contribution. So that's fine. But you mentioned that you have time-dependent curvature, and this can possibly not violate the null energy condition. So do you think there's possible? Yeah, go ahead.
Yes, it's not related to the wormhole. It's just it's just a curvature that it's attached to the warp drive, similarly to the Van den Broek metric, if you've heard about it. So it's a sort of pocket in space-time that moves with the warp drive. And yes, our back of envelope calculation says that it does much better than the standard warp drive metrics, but more thorough analysis is needed to say anything for sure. I would say, given all this amount of negative results, I would take it with caution. I would not make too loud statements for now, but what I'm saying is that we need to look further into warp drives with non-zero intrinsic curvature in general. I believe it's a promising avenue.
Okay, thank you.
I had been working with wormholes a long time ago, so you make me feel younger than I am, and I appreciate that very much indeed. I would have just a general question, and then, if you let me say, I would like to meet you in Bergamo, which is not far from Turin, my town, and so we can keep going on the mathematics at least. So the question is this one. Did you use a symbolic manipulator for instance, for computing the Kretschmann invariant and complicated expressions like that? And which one is that? Or can you make a comparison between, for instance, Mathematica, Maxima, and Maple? Thank you.
Well, I did indeed use a package called OGRE, made by Barak Shushani, a former student at Perimeter Institute. I did indeed apply this package to compute the Kretschmann scalar. I also experimented with Maple, but in my personal opinion, this Mathematica package is more reliable. Maple kept giving me the packages in Maple are older, they are more outdated, and they kept giving me a strange result. So honestly, I would recommend Mathematica to everyone.
Okay, thank you very
But
much,
this
and
was
see you.
um,
See
I
you
would
in
really
Italy
like to
sometime.
meet you in person. You can You can write to me on email and we arrange a meeting.
Yes, very good. Thank you very much indeed.